Chapter 8, slides 31 to 48. What you'll notice is that there's a lot of practice slides on this section. So we're not going to go through a lot of these slides together. The first few are some more practice doing elimination reactions, or E1. So we're telling you here to do E1 mechanisms on these samples. And in this next slide, again, we're asking you to do elimination reactions, not substitution reactions, elimination reactions, but you're going to have to decide whether you want to do E1 or E2. This next slide again asks you a question about this given compound and why only a substitution product and no elimination products are observed when this compound is treated with sodium methoxide. So I'll let you guys ponder those 3 slides and get more practice in. I want to talk a little bit about the competition between all of the mechanisms we've been discussing. So it's important to be able to consider all 4 when you're given a system. Now, I would say that the first thing you're going to do is look at, E2 versus SN2 versus SN1 versus E1. Now, the key here is to be able to distinguish, at least break it down to a 50-50, right? Are we talking about substitution or are we talking about elimination? If you're given the molecule shown, you'll see that it's a secondary chloride. That doesn't tell us much. It doesn't help us understand whether I'm going to do any of those 4 mechanisms. So I got to dig a little further. Let's look at the conditions. Well, they're giving me methanol. I am now deciding that this is going to undergo SN1 E1. As such, I'm going to show what would happen if I just had done substitution, but SN1 substitution. The products are going to be forward OCH3 and back OCH3. I'm going to get a mixture, in this case, of enantiomer substitution products. The elimination product, had I considered E1, and I should, this is going to be the major elimination product. There are going to be minor ones, but the major substitution products are shown and the major elimination product is shown. It's important to go through this for each one. In the second case, I have a secondary chloride. The conditions given are sodium methoxide. Now this is strong, so I'm going to consider SN2 and E2. Doing that, I get the substitution product of back OCH3 only, and the elimination product of trans 2-butene. Why am I going through this? Well, it'll become a little bit more evident in the next slide. Let's look at the third case. I have another secondary system, could undergo anything at this point, so I've got to turn to the conditions, and I'm going to consider both SN1 and E1. These are weak protic conditions. In this case, the major product or products, in this case, is going to be OCH3, this ether. However, the major product is going to be the one after a carbocation rearrangement has occurred. You guys can do this out, do the mechanisms out for these. And you'll see that this is not a chiral molecule. It doesn't have a stereocenter. So there's only one major product for this SN1 substitution. The elimination is going to yield also one major product. And it will be this alkene. The last case, again, secondary chloride. I turn to the conditions given, and I'm going to consider both SN2 and E2. The O minus in a substitution is going to backside attack. I should say opposite side attack. Nothing happens at the methyl position. But the opposite face attack of this species gives us a forward OCH3, and that's the one major substitution product for the last case. Note that the hydrogen next door in one direction for the elimination, the E2 elimination, can never be anticoplanar. The only one that can be anticoplanar is the one drawn on the other side. This hydrogen that I've boxed off is the only anticoplanar hydrogen available to that chlorine. Therefore, the only E2 product for this system is as shown. Now, why did I go through this? Could I have identified what the major product would have been between the substitution elimination products? So notice that what I did as I went through this and I broke it down, I was able to tell you if you were going to do SN1E1 or SN2E2. Now for all the SN1E1s, if you recall, you can't distinguish. You're going to get a true mixture of SN1 and E1 products. You can't help it. So in these scenarios, for the first and third scenario, you're going to get a mixture of those substitution and elimination products because it's very tough to favor SN1 over E1 because they're the exact same conditions. However, there are differences between SN2 and E2. And I would guess that in the second case, SN2 would prevail, giving you the major product of the substitution product. Why? Well, you're on a secondary system. It's pretty small. And the sodium methoxide is actually pretty small as well. And so I'm sure that you're probably going to favor the SN2 in that case. Likewise, at the last one, again, you're using a small base or nucleophile. And so it's really probably going to favor this SN2. If I wanted to favor the elimination, I might want to bump up the steric bulk in order to favor that E2 a little bit more. Let's take this to the lab where we can get some actual data. So in this first case, what you'll notice is that we're giving you a 90 to 10 product distribution. They're both this is the substitution product, and this is the elimination product. And what you want to rationalize here is, first of all, what type of substitution elimination was it? Given that the alkyl group was primary, the alkyl bromide was primary, and your nucleophile is small and strong, I would think this is SN2 or E2. But I would favor SN2 because all of these small, strong nucleophile with a primary bromide, this is definitely favoring an SN2. And that's exactly what we see experimentally. So for further practice, it's good to be able to draw both of what you expect, because if you were running this reaction and then you went to the instrument lab and you saw that you had a mixture, right? Because what's the relationship between these two molecules? They're not even isomers of one another. They're two completely different molecules. So, you're going to get a TLC with two spots on it with different polarities. And then maybe you separate them. And then you run an NMR. You're going to see that one of them is what you expect, because maybe you intended to do an SN2, but what's this other molecule I created? It's nice to know and anticipate the byproduct that you might see, right? This is a side reaction that is just not what you want. You're probably going to have to throw it away, maybe. But, it's nice to predict what other things could happen. And the vinyl hydrogens off of this system will be very distinguishable on an NMR. So it's nice to have some idea to predict other things that could happen and form in your system. I'll leave the rest of these for you to do. First, figure out if they underwent an SN1 or SN2, E1 or E2, and then try to rationalize why you see the product distribution that you see. And we have a few slides of these. One of the things that is important, I'll say it again, is that the SN1 and E1 really cannot be teased apart. Sometimes you can heat a reaction to favor an elimination, driving water off, and Le Chatelier's principle will allow you to move more towards the elimination product. But again, it's when you see SN1, you typically see E1 as well. So let's take a look at our now completely filled in substitution elimination summary chart. We can not distinguish between SN1 and E1 because everything is exactly the same. Everything's the same. Protic systems, tertiaries preferred. Good leaving group is a good leaving group. Rearrangements are common because you form a carbocation. How about the differences between E2 and SN2? Well, this is the major difference right here. The tertiary is preferred for E2 in conjunction with a strong base, and I would say it's even favored when it's bulky. You can add the word bulky here. That really is going to favor that E2 mechanism. You still need a strong nucleophile for SN2, but you really need to avoid steric hindrance. So E2 and SN2 can be teased apart. So you should be able to say I have an E2, or I have an SN2, or I have SN1/E1, right? We're going to kind of group those together. Another handy chart, in case you want to understand sort of a process, this is a little bit more detailed, and it goes through step by step what you should look for. So, if you're looking at your electrophile first, this is a good thing to see. Is it primary, secondary, or tertiary? Then once you identify, like let's say it's tertiary, then you're like, okay, well, it could be SN1, E1, or E2. Then you want to look at the nucleophile/base. If it is strong, then you're going with E2. If it's weak, then you're doing the SN1/E1. Notice that the SN1/E1 is always together. You can't distinguish between them. So, nice little chart to help you along, especially when you're not given the mechanism to employ. Read the instructions of the practice problems. For this one, right, it's telling you it could be any of these. So first figure out what it is, state the mechanism in the box, and then do it. Calculate your product, your major product. Here, we're giving you the products, and we're asking you to think about which alkyl halide you could have started with. So we're making you work backwards on this one. That's a little trickier, right? Good mind gymnastics, though, for you. I can do one of these with you. Let's do B. B is interesting. Now, I want to show this one to you so that you're thinking a little outside the box. There are two different ways of thinking about this problem. Are you going to make a bond here, or are you going to make a bond here? Let's consider both and then take a step back and decide which one we like better. You could have said, I'm going to start with an alkyl bromide, and I'm going to add OCH3. This is secondary. I don't want elimination, so I'm going to try and force an SN2 reaction. forcing that SN2 reaction, I'd want a strong O minus. That way, the O minus kicks off, and I should get that as the major product, right? So really what I'm suggesting is that we take this cyclohexyl bromide, and add NaOCH3. What if, though, I had CH3 bromide and I added O minus with the cyclohexyl group on it? This is a methyl bromide, not a secondary, it's not even primary. The O minus would attack the carbon and kick out the bromine. Which one do you like better? Which one do you think, from a rate perspective, from a more efficient perspective, will work better? If you said this second case, you'd be correct, because the SN2 reaction is happening at a methyl bromide, not at a secondary carbon. It is much harder, even though sodium methoxide is smaller, to be the nucleophile and come into that very crowded secondary cyclic bromide than it is for, even though this is a large nucleophile, that methyl group is super, super open for business, right? It is not sterically hindered whatsoever. So always understand that when you're designing, you have choices. No one's telling you where to make that new bond. You can decide. And there were two choices. I would have chosen to do it this way for efficiency. So I leave these practice problems open for you. And I'd like to now go to the IUPAC naming, which is the last thing we have to discuss regarding alkenes. So alkanes, as we mentioned, are saturated hydrocarbons. They're carbons that have the maximum number of hydrogens on them for that given number of carbons. Unsaturated hydrocarbons mean that they have either a ring or a pi bond. Therefore, since we've been talking about making alkenes, right, they're the product typically of the eliminations that we've been doing, we tend to make unsaturated hydrocarbons when we do elimination chemistry. So as a quick review, when looking at a molecule, we can very quickly determine the degrees of unsaturation for those molecules. Remember, degrees of unsaturation is 1 degree is either a pi bond or a ring. So if I look, I can see that there's a double bond there and a double bond there. So this would be a 2 degree of unsaturation molecule. B has a ring and a pi bond, so this also would be a 2 degree. C has 2 rings, no pi bonds, but each ring counts as a degree, so this is 2 degrees of unsaturation. And the last one has a triple bond. So this triple bond, there's 2 pi bonds and a sigma bond that make up the triple bond. So this is also 2 degrees of unsaturation. Now, to this point, we've been calling alkenes either cis or trans. And this is a flawed way of naming. This is not the IUPAC way of naming cis or trans double bonds. Here's why. Look at these 2 molecules that I've drawn here for you. How would you name them? Would you name them cis or would you name them trans? Kind of hard to tell, but you can definitively look at them and say that they're diastereomers of each other. They're connected in the same order, they have the same atoms, same molecular formula, but through space, their relationship to one another is different. They're not mirror images, they're diastereomers. So how do we do this? So I just want to quickly show you the nomenclature for when you have an alkene. So this is the proper way of naming whether a bond is cis or trans. Step 1, draw an imaginary plane bisecting the double bond. So I know some of you have done this already from homeworks, but I want to go over this process again. I call it the volleyball net. So perpendicular to the double bond, draw a line. Okay, I draw a dotted line. I don't know. I pretend it's a volleyball net. Okay, and then what you're going to do is each side of the volleyball net has two players. So I guess it's beach volleyball, 2v2. Okay, so you look at the first team on one side. I have a fluorine and a hydrogen. You're going to use the same priority method using atomic number, one atom out at a time, to figure out who has the highest priority. Who's the better player on your team? Well, fluorine has a larger atomic number. So fluorine is the better player on the left side of the net. That's my high priority group. Team 2 on the right side of the net, I've got chlorine and bromine. And if I look at the periodic table, bromine has the higher atomic number. That's my priority player. So when you look at them, they're not on the same side, right? They're not playing head to head. They're across from each other. Therefore, this first molecule would be given, which one? Z or E? The same side is called Z, opposite sides is called E. This is E. This is a German word. That's where we get E from, meaning apart. Let's do the same process to the molecule on the right. Notice that we have fluorine versus hydrogen again as our players on the left side of the net. Fluorine is again my priority group. I look to the right and I see that bromine is again my priority group because of atomic number. Now they're on the same side. When they are on the same side, we have Z. Do you get what I'm doing here? Z is on the same side. That's the way I remember it still. I kind of do that silly thing because I don't remember the German because I don't know German, but that's okay. E and Z. Here's some practice for you. You can rank each of the following according to their priorities. And then at the bottom here, you can name the following compounds. Let's do the second one together. I want to find the longest parent chain. 1, 2, 3, 4, 5. I also want to make sure that the alkene is included in that longest parent chain. I started numbering closest to the double bond, which takes priority. So this is a pen, longest parent chain. I've accounted for all of those carbons. A pentene. So that means the ene, not pentane, pentene, and that double bond starts at carbon 2. You'll also see sometimes people write pent 2-ene. Some people like to keep the number closer to the actual function. Either way is acceptable in my book. All right, what haven't we included? Well, we didn't include the methyl at 3 or the methyl at 4. So there's a 3,4 dimethyl 2-pentene. Okay, I'm almost done. I have to tell you about the geometry of that double bond. So if I draw my volleyball net perpendicular to my double bond, and I consider all 4 substituents, I look at the CH3 versus the H, the carbon versus the H, that's my strong player. I go to the other side of the volleyball net. I have carbon versus carbon, so I got to go out again. Well, the carbon on the bottom has 2 carbons off of it, and the carbon at the top just has hydrogens. So that's my stronger player, and they're on the same side. So I'm going to put a Z in front of this. So it's Z 3,4 dimethyl 2-pentene, or Z 3,4 dimethyl pent-2-ene. Either way, I'll leave the remainder for you to do. Here's some more practice for you. What happens when you have 2 double bonds? You can get a hint of what you do right at the bottom here, and that's the hint I'm going to give you, right? Try to maybe start with the bottom where you have to draw what they tell you to draw. And then you can go back up and name the ones that you see. What I want you to pay particular attention to is this double bond here in B. If you tried to name that double bond as E or Z, you wouldn't be able to. Draw your volleyball net. You see that those two H's off of the other side? How do you tell the priority? That's like not having a stereo center when you're doing stereochemistry. You just can't decipher. You'll never break the tie. Therefore, that double bond, it has to be part of the name as an ene, and you use a number to tell where that ene is, but you don't have to give it an E or a Z. It will be drawn that way no matter what because it has two hydrogens off of the other side. It doesn't matter how you draw that double bond. There is no E or Z conformation for it. These last few slides are more elimination practice. You have to do elimination and you either do E1 or E2. They don't want you to do the substitution for them. And in this one, again, is more elimination practice. Which one are you going to do? You're going to have to figure it out. E1 or E2. Provide the major elimination product or products.